Okay, students, thanks for tuning in. In this video, we're going to take a look at the history of energy use, coal formation, petroleum extraction use and future depletion, and natural gas extraction and use. So let's start with history of energy use. People have long exploited energy sources. Coal, oil, gas, solar, and wind power were all used to some degree before 1200 BC, whether to heat homes or to heat water or to cook food. And fire, animal labor, and hot springs were used long before that. But only since the Industrial Revolution, which started in the early 1800s, have we harnessed energy sources on a grand scale. So these are the energy sources used today. These first four listed are non-renewable: crude oil, natural gas, and coal. Those are all fossil fuels. Nuclear energy is also non-renewable because it relies on mining uranium. And these other ones here, biomass, which is like plant matter, hydropower, solar energy, wind energy, geothermal energy, and tidal and wave energy. These are all renewable. How do fossil fuels form? Well, they are highly combustible substances formed from the remains of organisms from past geological ages. And then the compressed tissues of plants and some animals, and actually a lot of phytoplankton from 100 to 500 million years ago, store chemical energy from photosynthesis when they were alive. And this greatly concentrated energy is released when we burn coal, oil, or gas. So here's a little diagram of this. Step 1, plants and animals die. And here we see that happening in both terrestrial and oceanic ecosystems. And terrestrial meaning swampy. So then the organic material settles in an anaerobic state and is partly decomposed. So here we see these organisms dying and sinking. And the same thing with the wood, will die and fall into the swamp. Now in the next part, there's a key element here, and that is these words, accumulating sediments on both sides. Because of that, you get anaerobic conditions, because the decomposing material is underneath the sediment. And so because of that, you end up not getting it biodecomposing into CO2 and H2O like normally happens. Instead, you have things like methane forming, or petroleum, or coal. And so from that, in what were formerly swampy areas, we tend to get coal formed. And in what were formerly oceanic areas, we tend to get crude oil and natural gas formed. So the difference being that it's woody terrestrial vegetation, which generally leads to coal formation. Alright, so organic material is buried. Heat and pressure alter the chemical bonds. Okay, those are the basic steps there. And it's formed. We can see that the use has been rising a lot, even just since the 1950s, for all three of these. And growth in coal has slowed, as you can see here, but oil and gas are still rising. And one of the principal reasons for oil rising is that we use it for cars, transportation. As far as the distribution of fossil fuel reserves, Saudi Arabia has the most oil, and of course it's in the Middle East. Russia has the most natural gas, and the US has the most coal, but China uses the most coal. And you can see the countries that are in second place here: Iran for oil, Iran also for natural gas. So they are making a lot of money by exporting that. And they're also in the Middle East, and then Russia being very high in coal as well. You should know these, by the way. Per capita energy use varies. You can see that the US and Canada, we have the highest energy consumption per capita per person. Heavy energy users. And also in the Middle East here, Saudi Arabia also having very high energy use. Remember, they also use a lot of energy for doing desalination. Since they are a desert area, they use their saltwater resources to make fresh water. And the lowest energy use per capita, Central America, South America, Africa, and regions of Asia. We can say Southeast Asia. This is how the US uses electricity by fuel. And I took this question off assignment 9.1, but you really should be familiar with it, so I'd like you to jot it down. We get most of our energy from coal. Second place would be natural gas. Third is nuclear. This is specifically for generating electricity, not for running our cars. So you can see that all these renewables are actually a pretty small slice of the pie. In California, we get most of our electricity from natural gas. We have really good reserves off our coast here, and we also pipe it in from Mexico. Let's take a look at coal. Pretty messy stuff, as you can see here from this coal miner. It's the plant and microorganisms remains compressed under high pressure to form dense carbon material. So it's dense, it's a solid form. And it's first used 3,000 years ago. Powered the Industrial Revolution in England and then in other countries. So those first steam engines that were developed running on coal, like train engines. And today it is surpassed by oil, but is still the most abundant fossil fuel. And it provides a quarter of the world's commercial energy consumption. And right now, the country that's building the most number of new coal-fired electric power plants would be China. And so here's another sort of close-up on how coal is formed. Here's our ancient forest, and this is showing increased time and decreasing moisture and increasing heat and pressure. So in the first stage is called peat, and this is sort of like partially broken down vegetation, and then it becomes lignite, and then subbituminous coal, and then bituminous, and then anthracite. And you'll notice that it's getting deeper as time is increasing. There's more sediment piling up on top of it, and with more increasing heat and pressure, it's kind of getting focused down into a more compressed form, and more very importantly as well, is it's having less moisture remaining in it the longer it decomposes. So anthracite is the grade A coal. That's the best stuff. It has the least amount of moisture, and also the least amount of sulfur, and it's the most dense, so you can get the most energy per kilogram of it. And because it has the least amount of sulfur, it's also the least polluting. But in many parts of our country, like in Pennsylvania, most of the anthracite has already been mined, so now we're using more of the lesser grade coals. And how coal is formed: so peat is partially decayed organic matter near the surface, and it becomes coal as it gets heated and compressed over time. And with more time, more moisture is removed, and the coal becomes more energy dense. And as we said, anthracite is the most compressed and most energy rich type of coal, the best stuff for burning. So these are the top producers and consumers of coal. China, interesting, we said earlier that US. Okay, so the difference here is we're saying that China produces the most amount of coal. In the US, we have the most amount of coal in the ground as reserves, but they're actually extracting more of it and making it ready for use in power plants. So you can see here they're producing the most and they're using the most. We're producing the second most and we're using the second most. So coal mining is not a simple thing here. We have two main types that we do it. Subsurface mining is where you traditionally, you go down into a deep mine shaft or deep in the earth, maybe not necessarily super deep, not like maybe a diamond mine where you might go deeper in Africa, but you're trying to access these seams, and so that would be those layers of all that heat and compression was was creating the coal. And then you can also have surface mining, or what we call strip mining, where you're just removing the top layers of earth to access those coal seams. And so there's a lot of dangers that go with the subsurface mining, because, number one, these could break, these could collapse, and people can get trapped, as we saw happening in the news every few years. Not to mention the air quality in here is extremely bad for the workers, so they have to have some kind of a ventilation system, as you can see here. But subsurface mining is safer for the actual miners, but it's worse for the environment. You have a lot of exposed rock, and that exposed rock does contain sulfur, and when it interacts with the water and the air, it creates sulfuric acid, and so that can contribute to acidifying different waterways. And we call that acid mine drainage. Let's look at how we make electricity from coal. It's a pretty simple process in a way. You take coal, you burn it, it goes into the furnace, produces energy, heat, and that heat boils the water, and that water is now in the form of steam, very high pressure steam, and so it's like sort of like wind going through this turbine. And this turbine, they're like fan blades. As they spin, they're turning the generator, which makes your electricity. And then that steam goes into the condenser, where it condenses back into liquid. And that's because the condenser is cool, and it's cool because it's bringing in cold water from a nearby river or ocean. And then that steam that was condensed goes back into the furnace as water, and the cycle repeats again. So this cooling tower, we often associate this shape with nuclear power plants, but all electric power plants that use heat to make electricity have these, and this is just a way for cooling down your cooling water before you release it back into the river or back into the ocean, because if you didn't, you would have an issue with thermal pollution. So when you see coming off the top of these, there's often usually really white smoke because it's mostly just steam. And the actual pollution from burning the fossil fuel is coming out of this pipe right here, and it's going into first a filter, and that filter is removing some of the particulates, and then it can also goes through something called a scrubber, which can remove sulfur oxides from the exhaust, and that can reduce the amount of sulfur oxides you're putting into the air, and those can cause acid rain. And then you have this ash, which eventually gets disposed of in a landfill. So you should know these general parts and what they do. Let's talk about oil a little bit here. Also called crude oil or petroleum. It's a sludge-like mix of hundreds of types of hydrocarbon molecules formed from temperature and heat over time, and it's found 1 to 2 miles below ground. And oil refineries sort the various hydrocarbons of crude oil, separating those to be used in gasoline with those used for other purposes like tar and asphalt, which we use for roads. The history of it is that it was first used 4,000 years ago in the form of surface tar or asphalt. In fact, at UCSB, they have some old mines there that are asphalt mines. You know, along our beaches here, we have oil seepage, and so there is natural oil under the ground, and that oil was mined as asphalt for making roads and things like that. But modern extraction began in the 1850s in Pennsylvania, and today oil is the world's most used fuel. So these are the top producers and consumers. Saudi Arabia produces a huge amount and exports it around the world and makes a ton of money. And the U.S. is the biggest consumer. We consume 25% of the world's oil. And you can see China is second, and Russia is also the second producer there. In the U.S., you know, we're third in production, but first in consumption. So right there, you know that we're importing a ton of oil. So here's a little diagram of oil drilling, and we're going to talk about primary extraction, which is the initial extraction. It's very easy because it just uses air pressure. So the basic idea here is that you just drill a hole, and this is kind of like your artesian well, which has its own pressure that brings the oil up to the top, or if that would be called a gusher actually, and that's somewhat a rare situation. But air pressure, we see when you drive along and you see oil pumps doing that back and forth seesawing or teeter-tottering kind of thing. That's using air pressure, creating a little vacuum up here, which sucks the oil up, kind of like very much like a straw, just like a straw. But at some point there, you have to get a little more fancy with it, and that's your secondary extraction, which is forcing oil out by pumping water or gas into the rock to displace it. So, you know, there's that whole idea of rock, and then the rock contains oil in the pores. That's very much like an aquifer for water. And so when we had to get a little bit more fancy with it, we had to inject seawater, and that seawater pushes the oil, displaces it, so that it is what gets pushed up into your collection pipe. And you can also do the same thing with injecting gas into it, and that gas will also displace the oil. So this is pretty energy intensive. You're having to put a lot of energy into forcing the stuff down in there to get the oil out, and therefore the energy from the oil. So it's like output energy versus input energy. You have to put a lot into it with secondary extraction. And so we kind of talked about most of this already. All right, let's take a look at some petroleum products. We normally think of petroleum as being used to make gasoline, and yeah, we burn it to get the heat from it, but we also use it to make plastics. And here you see a huge number of things that are made of plastic, or even paraffin waxes, so candles, things like that. And here's a little diagram. You don't have to know a lot of details about distillation, but you take this crude oil, which is a mix of a huge number of different oils, some which are very heavy and thick, like motor oil, and some which are very thin, like butane. If you ever look inside of a cigarette lighter, you can see the oil kind of rolling around in there. So the basic idea is you heat it, and as it's heating, it evaporates. And the parts that are lighter, they evaporate further up before they finally condense back, and then you collect them as a liquid. And so you end up getting small chain hydrocarbons, which boil at cooler temperatures. They are going to be higher up near the top. And your long chain hydrocarbons, they boil at hot temperatures, so they end up staying near the bottom. And we have a lot of uses for crude oil. About half of it we use for making gasoline. About a quarter of it we use for making diesel fuel and heating oil, which we don't use in California, but they use it back east. And jet fuel for airplanes. And then you can see other products would be like plastics. So we should talk a little bit about peak oil here. We may have already extracted half of the world's oil reserves, which is estimated at 1 trillion barrels. And a barrel is about 55 gallons. And to estimate how long this remaining oil will last, analysts calculate the reserves to production ratio, and they divide the amount of total remaining reserves by the annual rate of production. They get a graph that kind of looks like this, and this was for the U.S. crude oil production. There was a guy named Hubbert, and in the 50s he predicted, based on his analysis, that the U.S. was going to reach a peak in oil production in the 70s, and in fact that's what we saw. And so the red is what he predicted, and the blue is what actually occurred. And so we're trying to do a similar prediction for the rest of the world's oil. This is actual data leading up to the present day. So to the right of this is forecasted, but we can see that almost many of these countries did reach peak oil. Here, this is the U.S., at least the lower U.S. reached this peak in the early 1970s. And so we can see that oil production has decreased a bit recently, but is it really going down like this, or is it going to do some other thing? We don't really know for sure. But we do know that we are using a lot of oil. This is oil consumption in thousands of barrels per day. So the U.S. Is around 20,000 barrels per day. Sorry. So this is 20,000, but the unit is 1,000. So 1,000 times 1,000 is actually 1,000,000. So we're using 20 million barrels of oil a day. I mean, just think about that number for a moment. 20 million barrels of oil every day used in the U.S. And you can see Europe also, heavy user of oil, Asia and Oceania. And are we using it as fast as we find it? So that's the big question. Oil field discovery, this is where we discover new land that has oil underneath it. So you can see that we have seen a decline in discovering new oil, and the reason that we've allowed production to increase is partly because we've gotten better at learning ways of extracting more of what we have down there, more of what we know about. And here's U.S. crude oil production and imports. So the production of it has decreased in the U.S., but the importing of it has consequently increased because we need to meet our demand somehow. And this is just showing most of the oil starting from the Middle East and going out to these other regions, including all the way over to the U.S. So think about how much energy it takes to transport that halfway around the globe. And we see Russia supplying a lot of the oil to Western Europe. Should we drill in the Arctic Refuge? The Arctic Refuge is about 7.7 billion barrels over 50 years of production. That's how much we estimate we could get if we did drill for oil there. And the projected U.S. consumption, it's a pretty small piece of the pie, let's put it that way. So there's a big question, should we disturb that wildlife area for getting a relatively small amount of oil? Just a little graph here you might like. Are we here or we are here? Is it a question mark or a statement? We don't know. So let's finish up here with natural gas, which is primarily methane, CH4, and it is produced by anaerobic decomposition of organic matter by bacteria. History of it: the seeps have been known for 2,000 or more years, and it's used for street lighting in the 1800s. So you can see here people had to go around and fill up or light the lamps each night. And it became commonly used after World War II once pipeline technology became safer. And that's one of the biggest challenges with using natural gas, is having a way of transporting it without it leaking. And here we see Russia and the US and Canada. They're the biggest producers of natural gas, and the US being the biggest consumer, followed by Russia and then the UK. And the gas initially comes out on its own from natural pressure, but later it must be pumped out. And here are some of these horsehead pumps to extract the natural gas. So again, pumping it out means you're using these pumps to create a vacuum, like when you suck on a straw and then the gas comes up. All right, that's the end of part 1. Thanks for tuning in.